Welcome to the Scientific Sense podcast, where we explore emerging ideas from science, policy, economics, and technology. My name is Gill Eapen. We talk with world's leading academics and experts about their recent research or general areas of topical interest. Scientific Sense is an unstructured conversation with no agenda or preparation. We cover a wide variety of domains where new discoveries are made and new technologies are developed on a daily basis. We are most interested in how new ideas affect society and help educate the world how to pursue a rewarding and enjoyable life rooted in science, logic, and information. We seek knowledge without boundaries or constraints and provide unedited content of conversations with researchers and leaders who love what they do. A companion blog to this podcast can be found at scientificsense.com, and this podcast is available on over a dozen platforms and directly at scientificsense.net. If you have suggestions for topics, guests, and other ideas, please send them to info@scientificsense.com, and I can be reached at gill@eapen.info. My guest today is Professor Jeremy Darling, who's a professor of astrophysics at the University of Colorado, Boulder. He studies black holes, galaxy evolution, and cosmology, mostly using telescopes, but sometimes just by thinking. That's a good way to do it, Jeremy.
Thank you.
So I want to start with one of your earlier papers entitled Toward a Direct Measurement of the Cosmic Acceleration, in which you say the measurement of secular redshift drift can directly determine the cosmic acceleration and the history of expansion in a model-independent manner, and has recently been explored in the context of dark energy and large aperture optical telescopes. So what is secular redshift drift?
To talk about that, we need to go back to the basic idea of the universe is expanding.
Yeah.
And we call that the Hubble Expansion because Edwin Hubble discovered this expansion. And the idea is that we're in an expanding universe. The space between galaxies is growing. And so galaxies are moving apart from each other, just like in, say, a rising dough sprinkled with raisins.
Yeah.
If the galaxies are raisins, they're all moving away from each other. But if you put anything into the universe, stuff like matter or even light or energy, it creates gravity that slows down that expansion. And so for a long time, decades, it was thought that the universe's expansion should be slowing down because gravity is pulling things back together. It's just as if you throw a ball up in the air, it may be moving away from you, but it's slowing down because of gravity.
Right.
And so the idea is proposed quite a long time ago by Alan Sandage was that if you could measure the recession velocities of galaxies, that's the expansion velocity, and you can measure it over time, you should see it decrease. So you should see a deceleration of the universe. And that's what we call the cosmological redshift. It's just that the light coming to us from distant galaxies gets stretched out because the universe is expanding, it gets redshifted.
Yeah.
But we should see that redshift decrease. That was the thought. And that's what we mean by a secular redshift drift. Secular just means constant or steady over time.
Okay.
Then dark energy was discovered, which threw a wrench into the whole works. And what we have learned since is that dark energy is causing the universe to accelerate instead of decelerate. And remember, if you put anything in the universe, including regular energy or matter, it causes a deceleration. But dark energy has this very counterintuitive way of causing the universe to accelerate. So it's accelerating the expansion, but only recently. But the method that we're talking about still applies, is that if I could measure the velocities of galaxies very, very precisely, and then maybe wait 10 years and measure them again, depending on how far away they are, they'll either show us an acceleration or a deceleration. And this is a way to measure what's in the universe, how its expansion is changing, without having a concrete model for the universe. So that's what we mean by a model-independent measurement.
Okay, so drift here is really the change in redshift.
That's correct.
And so dark energy recently in a dark energy dominated universe, we find that the universe is accelerating. So this would imply that the redshift is increasing.
It should increase. That's right.
Okay, and so is that what we are finding though, from the measurements?
So we have not been able yet to measure this effect. It's a tiny effect. And to get a gauge for how small it is, you can ask, over what time period does the universe change dramatically? And that's roughly the age of the universe.
Yeah.
So if I lived a very long time, say a billion years, I could see the universe changing over my lifespan. But we don't live that long. We live for only maybe 100 years if we're lucky. And so we can substitute that sort of longevity for precision of measurement. But to make the measurement, we need to, if say we want to make the measurement in 1 year instead of a billion years, we need to be making measurements that are good to about a part per billion or better. So we need to measure the redshifts or the velocities of galaxies extremely, extremely well. And in fact, less than a centimeter per second per year is the rate at which we expect the redshift to change. So centimeter per second would be a velocity. We'd expect that to change by about 1 centimeter per second over the course of a year.
Right. So the further out we look, the higher the redshift and the faster they are moving. So I would imagine purely from an engineering perspective, you want to look as far away as possible?
Not necessarily, no.
Okay.
It's a little complicated, but it turns out that if I look at somewhat nearby galaxies, sort of medium redshift, we'll see that acceleration caused by dark energy. But if I look at very high redshift, very distant galaxies early in the universe, they will be decelerating because at that time, dark energy didn't matter too much.
Oh, I see. Yeah.
So the universe went through different stages in its life, and early on it was matter dominated, where the gravity was winning. But now today it's dark energy dominated, where the dark energy is winning. And in fact, because we go from today accelerating to in the past decelerating, there's actually a point in the universe's history where it's doing neither. It's right in between going from decelerating to accelerating.
So for this particular measurement, Jeremy, is there a sort of an optimum distance you want to look at?
Optimally, you would look at sort of galaxies maybe halfway back to the Big Bang, to measure dark energy. And then you'd look at galaxies much closer to the Big Bang to measure the deceleration. So there's two sort of distances that one would want to use.
And we are using sort of the same instruments that we use to measure redshift?
Yes, you can. And in fact, folks are planning to make this sort of measurement. It'll take decades, but using upcoming 30-meter aperture optical telescopes on the ground. This is one of their science cases that they're making. And what they'll do is measure clouds, in fact, between galaxies, measure the redshifts and monitor them over a few decades.
But the status quo, Jeremy, is that there isn't much doubt, right, that the universe is expanding and dark energy is causing it?
That's correct, but we don't know what the dark energy is, and we don't really know how it works. We're starting to constrain its properties. We call that the equation of state, but it's just its basic properties. But in general, the way we study dark energy now is to look at things we call standard candles or standard rulers in cosmology, where if I know how bright something is and I measure how bright it looks, I can figure out how far away it is. That would be a standard candle. And those things are very handy. That's what has revealed the existence of dark energy. But they all have their own specific issues in terms of possible systematic effects, and they also rely on something we call the cosmic distance ladder, where we sort of build up rungs of this ladder going step by step. But it's a rickety ladder, and so the idea behind the redshift drift measurement is we can skip all that stuff, and we're just making a direct measurement of what the universe is up to dynamically.
Okay. So you have a paper here that is sort of related. The Hubble expansion is isotropic in the epoch of dark energy. You say the isotropy of the universal Hubble expansion is a fundamental tenet of physical cosmology, but it has not been precisely tested during the current epoch when dark energy is dominant. We talked about a little bit about that. So the puzzle, I don't know if it's a puzzle anymore, but at least the question is, why is it so uniform? Is that the question?
That is the question. And we, until recently, have had to assume that the universe is sort of the same in every direction, and it's also expanding at the same rate in every direction.
Yeah.
But that has been a built-in assumption. That's changed a little since that paper was written. But the idea there was to just look around the sky, and if the universe is expanding anisotropically, in other words, not the same in every direction. Isotropic means iso, same, tropic, direction.
Yeah.
So if the universe is not expanding at the same rate in every direction, what you'll see is galaxies streaming toward the directions of faster expansion and away from the directions of slower expansion. And so that's what this work was looking for, was to see if we see these streaming motions, galaxies moving across the sky instead of strictly away from us, which would indicate that there's places in the universe that are moving away faster than others.
And did we find any such phenomenon?
No. And there have been some studies since using supernovae. Those are standard candles, once again, exploding stars, but they have a specific brightness. People have examined those as well and not seen any such effect. So it looks like down to maybe 5% or so that the universe is expanding at the same rate in all directions. And this is interesting because dark energy doesn't have to do that. There are models for dark energy that could give it some directionality.
So this is not explained by inflation, right, per se?
That's correct. So inflation happened in a very, very early universe. And the expansion today is unrelated to that.
Okay. And so the reason, so when we see this so consistent, what's causing it? Is there does this come out of the standard model, or does it create some questions?
The isotropy?
Yeah, the isotropy.
Yeah, it's sort of what you would expect in a universe that has no preferred locations or directions. We assume we're not in a special place in the universe, and we also assume that there are no special places at all anywhere. And under that assumption, if the universe were not expanding at the same rate everywhere, you would wind up with special places and not so special places, because there'd be regions that empty out and regions that concentrate.
Right. Okay.
So we can make basic observations today, just say counting galaxies. And if you take a big enough patch of the universe, it looks the same as other equally sized patches. Right. And that would also not be true if the universe had been for a while expanding anisotropically or differently in different directions. But dark energy only took over recently, so it's possible dark energy could be doing something interesting or strange.
So Jeremy, it is true that we are at the center of the universe.
It is true that we're the center of the universe, and everywhere is the center of the universe.
Right.
Yeah.
So I want to jump into another paper, 2017, how to detect inclined water maser disks, and you say, and possibly measure black hole masses. So what exactly is a maser? What's a water maser disk?
Yeah, a maser is a microwave laser. I think people are pretty familiar with lasers. And a maser, the M just stands for microwave instead of light. So it's just a different form of laser. But masers can occur naturally in nature, in space, in fact, in the medium between stars and also in stars, in the atmospheres of stars. There's even an infrared type maser in the Martian atmosphere caused by carbon monoxide. But so it's a similar phenomenon that we're used to with lasers, in the sense that lasers, when they occur naturally, they can make a beam of light that comes out of some gas. And if you happen to be looking in the right direction, it looks incredibly bright. You shouldn't, as we know, you shouldn't look at a laser directly because it concentrates so much light that you can deliver too much energy to your retina. With telescopes, it's fine for us to look directly at lasers. So it's mostly molecules that make these microwave lasers in space. And one of the most prodigious maser maker is actually water vapor in space.
But this is a microwave, so we won't be able to see it.
That's correct. But the frequency at which this maser occurs is exactly the same frequency that your microwave oven uses to heat food, because your microwave oven is exciting water molecules in your food. And that's exactly the same process that causes these natural masers in space.
So if the water could create, so you talked about Mars, where carbon dioxide causes the maser-like phenomenon. Here you're looking at water doing the same?
That's correct.
And so what's the connection to the black hole masses here? So is this, are we talking about closer to the center of the galaxy?
Yes, so there's a famous nearby galaxy. Let me step back. So galaxies, typically, we think most galaxies have massive black holes in their centers. So each galaxy has a very large black hole in its center, more or less. And there's a famous nearby case where in the disk of material that's orbiting that black hole, very close to the black hole, is water vapor, and it's making these water masers, these lasers in space, that illuminate for us this disk orbiting that black hole. And if I can observe any material orbiting a black hole, I can use just the sort of basic way that we, for example, measure the mass of the sun by looking at the orbits of the planets. We can measure the mass of the black hole by looking at material that's orbiting it. And these water masers just make it very straightforward to do that, and are also give a very precise way to measure the mass of a black hole.
So is the water vapor acting more like a prism or a lens or something like that here?
It is not. It is excited, so it excites internally. And then when it de-excites, it emits this very specific frequency for the maser. And then that frequency that light that's emitted finds another water molecule that's ready to go, that's excited, and causes it to de-excite. This is called stimulated emission. And that's part of the laser acronym. Lasers stand for light amplification by stimulated emission of radiation. That's what the word laser comes from. So you have one photon coming out of a water molecule that finds another water molecule, and you get two photons out where one came in. And each of those photons will then go and find a water molecule, and I go from 2 to 4 and so on. So I keep doubling the number of photons or light. And that's how you make this sort of cascade that creates this very unusual natural maser in space.
And the reason, how could we measure the mass of a black hole from there?
Yeah, so what we do is we look at these what they look like to a telescope, a radio telescope, are very bright spots. But you can also, they're very narrow in frequency. So they're monochromatic, just like a laser. Like a red laser is very red. It's one color of red. So we can measure these, the frequency and the position. And by measuring the frequency, we can measure the Doppler shift, or the velocity of these masers. And by measuring how fast things are moving around an object, we can measure the mass of that object by just doing orbital dynamics. So Newton could have done this. And so we watch this water vapor circling the black hole, and by seeing how fast it moves and how far it is from the black hole, then we can measure the mass of the black hole.
Yeah, it's counterintuitive to think about water vapor near a black hole.
Yes, well,
but it is.
Yeah, water is a hardy molecule. You know, there's water in sunspots. There's water vapor in sunspots on our sun, because it's just cool enough that you can form that molecule, even though it's 5,000 Kelvin.
And so have we done this for the supermassive black hole we have at the center of the Milky Way galaxy?
We have not. We use stars for that. So people have observed, and in fact, this was the subject of this year's Physics Nobel Prize, is two investigators, one in the States and one in Germany, observed stars orbiting the black hole in the center of our galaxy in order to, one, measure the mass of the black hole, but more importantly, to prove without a doubt that black holes exist. Our black hole in the Milky Way does not have these water masers or water vapor orbiting it.
And so where you have done this is somewhat distant galaxies, or where have you?
Yeah, that's right. So people have been searching for these water maser disks around black holes for a few decades now, and they found maybe a dozen of these. The work that you're talking about that I did is not to find new ones, but to show that, in fact, that water maser, if it's behind the black hole, can be gravitationally lensed. So the gravity of the black hole will bend the light of that maser. So you think of a laser beam being bent, it'll bend that light and send it our way. And so we can actually see these masers in a wider variety of circumstances than what people have seen so far.
Okay, so do we have any different expectations of the galaxy or the black hole where we find this, since you're not finding them in high frequency, right? You're finding only on a dozen places.
Yes. So we think that you need very special geometry. We think that you need to be able to see this orbiting material. It orbits in a disk around the black hole, and we think that you have to be able to view that disk nearly edge on. So imagine holding a record, and instead of looking at the record face on, you hold it very edge on, so it looks very thin. So we think there's a geometry that's required. So we don't think that these are necessarily so rare, but that you have to get very lucky in terms of their orientation as seen by us.
Okay, so just a perspective. So it has to be arranged in such a way that we can actually see it.
That's right.
And so again, but still a dozen seems sort of a small number, right?
It is a small number. And this is a dozen with what we would call very organized disks of material. We found water masers near black holes in many other circumstances, but only a few that are so well organized that you can make these orbital measurements to measure the black hole mass.
Okay. We'll take a quick break, Jeremy. When we come back, we'll talk about a couple of your newer papers.
Okay.
This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com. So we are back. Jeremy, we are talking about a few of your previous papers in terms of the expansion of the universe and even how to measure the mass of a black hole using water maser disks. I want to go into a couple of your recent papers, and one of them is Extragalactic Proper Motions, Gravitational Waves and Cosmology. You say we review the cosmological and local phenomena revealed by correlated extragalactic proper motions, their expected amplitudes, the current best measurement, and predictions of Gaia. Gaia is the ESA satellite, right?
That's correct.
So what do you mean by proper motion?
A proper motion is an astronomer's strange term of motion that is across the sky instead of directly toward or away from us.
Okay. And so that motion allows us to think about gravitational waves?
Yeah, that's right. So people have probably heard about LIGO, the gravitational wave detector that was incredibly successful over the last few years. What LIGO does is measures the stretching and squeezing of space-time caused by gravitational waves. Gravitational waves are ripples of space-time caused by, for example, merging black holes. And so people are used to, or they're now used to, the idea that space-time will stretch and squeeze and sort of shrink and stretch a physical distance. What gravitational waves also do, though, is wiggle things back and forth. And so if I look out at a distant object in the universe, like a quasar or a black hole, or any bright object, if a gravitational wave were to pass by and I could measure it carefully enough, I would see that distant object wiggle back and forth.
Yeah.
As the space-time itself bends or stretches and squeezes, it will cause a distant object's light to follow a different path from the one in a sort of a non-bending space. And so what it looks like to us, it would be objects, if you look at many objects all across the sky, is they will move back and forth a little bit across the sky in a very regular pattern.
Okay. And so proper motion again. So this is something that is sort of moving perpendicular to our line of sight.
That's exactly right. Yes.
Okay. And so that movement makes it easier for us to measure this wiggle. Is that the idea?
The measurement is difficult, but we can make the measurement of a part of the gravitational wave spectrum that is not available to other facilities. So just like the electromagnetic spectrum, the spectrum of light that goes from X-rays all the way to radio waves and includes visible light, gravitational waves also have this huge spectrum where they can have many different wavelengths or frequencies or energies. And the LIGO experiment looks at a very specific, fairly high frequency gravitational waves. And as we move to lower and lower frequencies, you need different techniques for seeing these gravitational waves. And this method of looking at proper motions, so the motions of distant objects moving around on the sky, is very sensitive to very low frequency or very long wavelength gravitational waves. In fact, all the way down to wavelengths that are about the size of the observable universe.
Wow. And so these are these are very heavy objects. So supermassive black holes merging or something like that.
It's so supermassive black hole mergers would be hopefully detected by a facility that's upcoming called LISA, which is a space-based LIGO, space-based gravitational wave detector. That will be sensitive to low frequency gravitational waves caused by merging supermassive black holes. This method of proper motions goes even lower than LISA. So it's looking for gravitational waves not caused by black holes anymore, but caused by the very early universe. So it's thought that in the very early universe, there was a process called inflation that caused the universe to grow very rapidly that may also leave gravitational waves from the early universe that are just rippling through space-time all the time. And so this proper motion method would be sensitive to those types of gravitational waves from the very, very early universe.
Okay, so this could be sort of an alternative to the polarization technique that was used to look at, again, inflation from the South Pole.
Yes, that's right. So the other technique to measure these same gravitational waves is using the cosmic microwave background polarization. So the cosmic microwave background is that glow from the early universe, and that light is expected to be polarized, and the polarization can reveal on certain sort of size scales on the sky, it can reveal also that same primordial gravitational wave background from inflation. That's right.
And so this, again, if we are successful here, I don't know what the status of this is, Jeremy, but if you're successful here, this would prove inflation.
I think if you were to detect these gravitational waves, because there's no other method that we know to make them, it would probably provide very strong support for inflation, yes.
Yeah. And where are we in terms of these measurements?
They have been made. We did not detect any gravitational wave signal yet. I expect that they will continue to get better incrementally over the next 10 years or so. And then at that point, if we haven't detected them yet, I think it will become extremely difficult to do much better.
And so then it sort of casts some doubt on inflation again, potentially.
It doesn't really. So inflation is not a theory, but it's a huge family of theories.
Yeah.
And there are types of inflation that make a lot of very strong gravitational waves, and there are some that make much lower sort of energy in gravitational waves. So what this could potentially do is rule out some inflation theories, but not all inflation theories.
Okay. And the measurements here are all from Gaia or from some other sources?
The paper that's been published combined Gaia observations, which is visible light, and radio observations using the Very Long Baseline Array, which is a collection of radio telescopes that roughly span the size of the Earth. So we synthesize a telescope that is roughly the size of the Earth to get very high precision in measuring where things are.
Okay. And Gaia is still operating, right? So you are expected to get more data?
Yes. And part of that publication you were talking about makes predictions for how well Gaia will do when it reaches the end of its mission.
In a few years, you said?
That's right.
Okay, so I want to jump into another paper, Jeremy. So this is entitled New Limits on Axionic Dark Matter from the Magnetar PSR 11, PSR 1745 to 2900. You have to come up with better names, Jeremy.
Sure. Yeah,
So,
technical papers, yes.
Yeah. So a magnetar is a neutron star, right? With very high levels of magnetism. Is that the way to think about it?
That's right. Yes.
And
yep.
Yeah, go ahead.
It's a collapsed core of a massive star. We call a neutron star. And neutron stars, when they're born, they tend to spin rapidly, and they also have very strong magnetic fields. And there's an exclusive subset of these called magnetars that have truly outrageous magnetic fields. So they're the most highly magnetized objects that we know of in the universe.
And they're spinning rapidly.
Fairly rapidly. So the magnetar that's the subject of this work is not so fast. I think it spins maybe once every 3 seconds.
And so dark matter, there is still we still don't really know what it is. Generally speaking, 5% of the universe is matter that we know. 25% or so is what's called dark matter, and the 70% is dark energy. So that 25% of the dark matter, there are a lot of different ideas, different candidates, what might be dark matter. And this is looking into one of those candidates?
That's correct, yes.
So what's an axion?
So an axion is a particle that is a good dark matter candidate. There are a handful of different dark matter candidate particles. Generally, people think that, not all, but generally people think that dark matter is a particle instead of, say, rocks or failed stars or something else. And there are different classes of particles. The axion is one. I like axions because they were predicted to exist decades ago to solve another problem in physics, which is related to the neutron. The neutron, as your listeners may know, is made of 3 quarks of different charges. Whenever I have a collection of particles together that aren't sitting on top of each other, that have different charges, I should have some sort of charge distribution inside that object. And so the neutron should have what we call an electric dipole moment. In other words, one side of the neutron should be negatively charged, one side should be positively charged. But in laboratory experiments, they found, in fact, no electric dipole moment in the neutron. And this is called the strong charge parity problem, or strong CP problem. And the way out of this is to more or less create a particle called the axion. If the axion exists, it explains why the neutron does what it does and why it has no charge distribution. So the axion is predicted to exist to solve this particle physics problem. Very recently, some theorists realized that the axion could potentially also explain why there is matter in the universe. In the very early universe, we had roughly equal parts matter and antimatter, but about 1 part per billion extra matter. And so when matter finds antimatter, it annihilates and makes light, makes energy.
Right.
And so we had 1 billion parts of matter and 1 billion parts of antimatter annihilate each other and make 2 billion photons. And there was one tiny little piece of matter left over, and that's the material world we see around us today. And that little imbalance explained, but it turns out that axions might be the explanation. So if axions exist, they solve 2 big physics problems. And one's pretty profound, which is, why are we even here? Why do we live in a universe that has any material in it rather than just light? So that's why I like the axion. And the other thing is that if the axion exists, then it would also be produced in the early universe in abundance. And so it could also be dark matter.
So how does it, so is it a quark-like thing? It's a fundamental thing, right?
That's right. It's a fundamental particle, but it is not a quark. One of the properties of dark matter is that it makes gravity because it has a mass. So the axion has mass. The other property of dark matter is that it doesn't interact well with light. That's why we call it dark. So axions do that as well. They interact incredibly weakly with light.
And so what's the action inside the neutron to make that dipole expectation not realized?
That's a little complicated. It's called the Quinn-Pecci mechanism, and it just has to. It's fairly complicated, but it has to do with what are called mixing angles. And basically, you need this angle in there to be very close to 0. And there's no natural way to explain that unless you have a particle that's basically its job is to do that.
But we cannot really experimentally prove its existence, right? Can we?
There are experiments underway to try to detect the axion, either through detecting it as a dark matter particle or creating it. Either way will work. There's a really fun, brilliant experiment going on right now. And to explain that, I need to mention how axions actually do interact. They interact with light, but very weakly. And they only interact when there are 2 photons involved, 2 particles of light. And typically what that means is you need a very strong magnetic field. And if the axion passes through that strong magnetic field, it can be converted into light. Or you can shine very strong light through a strong magnetic field, and you may make some axions. Go ahead.
No, so just for my own understanding, so you need a strong magnetic field and the presence of 2 photons for an axion to be converted into 3 photons?
No, so you need the strong magnetic field provides 1 effective photon. Because remember, electromagnetism is light. So we need a magnetic field and in fact an electric field. But basically it's 2 photons can become an axion, or an axion and a photon can allow that axion to transform into a second photon. Sorry. But basically the magnetic field is providing one of those photons. And so when an axion encounters a strong magnetic field, it can either become a photon, or a photon encounters a strong magnetic field, it can become an axion.
But do we have an estimate of, we still have to explain 25% of the mass. So do we have an estimate of its, its frequency and its mass?
We don't. So the interesting thing about the axion is it's predicted that if it exists, it will be made in abundance in the early universe and can account for the dark matter. However, you could have many axions that are light, or you could have fewer axions that are heavier. And the theory does not predict the mass of the axion, which has been the trouble with detecting it, is people don't know where to look.
Okay. Yeah. And so the two varieties, they are orders of magnitude different in terms of masses?
So it's a continuous, big open range of possible axion masses.
Okay.
Yeah.
So, so in conclusion, Jeremy, so you look forward. I know that you're involved in a lot of this experiments. There's still nagging questions around dark matter and dark energy. What is your sort of expectations in 5 to 10 years, where we are going to be in terms of understanding it better?
So we'll start with dark energy. Yeah. I am not optimistic about that. What astronomers and physicists are doing right now is narrowing down the parameters of dark energy, but I don't see us really coming to grips with what it is or why it's there. So I think we will soon have a very tight constraint on its properties.
Yeah.
And it's like we'll have the outline of the elephant, but we won't know that it is an elephant or why it's there.
So it could trace back all the way to the Big Bang, so it becomes sort of a feature of the Big Bang?
No. In fact, dark energy, it only arises, we think if it is what we call a cosmological constant, it's been around forever.
Yeah.
So it would be some property of the vacuum. So if I had a vacuum, a pit of space with nothing in it, it should have some dark energy. So some sort of fundamental property of space-time itself. And it only becomes important when the universe gets big enough, which is recently.
So it's a property of the balloon, but it just shows up when the balloon gets to some size, and not the right.
It only becomes important.
No.
So you have to have a certain amount of empty space for this tiny amount of energy to matter.
Right. And it's a runaway process, right? So once it starts to accelerate, it's going to continue to increase that acceleration, right?
That's correct. Yes, and unless it is some field that decays and goes away, it should drive all galaxies apart from all other galaxies. And if you live sometime in the future, you would see a big empty universe.
Cosmology will be a lot easier then.
Or very boring, yes.
And what do you think about the dark matter? Are we making progress there?
I think we are, and I think this is where I'm more optimistic. I think that somebody soon is going to find at least a dark matter particle. There may be more than one.
Yeah.
But I really think something will be found in the next decade.
And Axion, as you mentioned, is the one that you like as a leading candidate. What are the other leading contenders for it?
The other main contender that's been most favored for quite some time is called the WIMP, the Weakly Interacting Massive Particle. So weakly interacting means it works through the weak force. That's how it interacts with other particles. But the parameter space, the area that you could search for WIMPs, is slowly being whittled down. And I think that fairly soon, physicists especially will either find it or decide that's not it. Yeah.
There is some sort of experiment going on to detect it, but we haven't found any yet, right?
That's right. There are many experiments happening right now.
Yeah. And so it's almost like the race is to find one. Whoever finds it will have a great advantage to establish that as what dark matter is. But I guess it has to fit the parameter space pretty well, right? Because we have an aggregate expectation of what that should look like.
That's right. And we also know that this dark matter particle is going to be outside of what's called the standard model of particle physics. So it's not some known particle. And I think not only finding this and solving this mystery will be exciting, but this will change particle physics once it's found.
What do you think? Will it make it easier to get gravity into some kind of comprehensive framework, or it'll make it more complicated?
I think it will only help for us to expand on the standard model, and we found these cracks in it, and to have at least one piece of the puzzle can only help in terms of uniting other quantum mechanics with gravity.
Okay. Yeah, this has been great, Jeremy. Thanks so much for spending time with me.
Of course, thank you very much.
Good luck with this research.
Oh, thank you.